There we go. Okay, hey everybody tuning in on the recording. So we are doing kind of our first night in real algebraic geometry. So if you haven't, go ahead, go back and watch the stuff on our topology and category theory stuff. And then right now we're gonna do basically Hartshorne chapter 1. So lecture, I guess 3? No, 4. Wow, you have really gotten into this. Okay. So I will add that Hartshorne's kind of a weird book. And it's really weird because it doesn't explain what algebraic geometry is until the end of the first chapter, when you've already done a really non-trivial amount of algebraic geometry. But this is actually pretty common because to really understand what it does, you have to kind of understand some of the tools that it uses. And so, yeah, I've just kind of found it to be helpful if one is willing to put aside the notion of having a big picture that we care about, and just kind of abstract mindlessly until the big picture reveals itself. Something along the lines of losing the forest for the trees for the sake of getting out of the forest. Um, so this is not something that comes super easily to most people, just as a mindset in general. And so I don't know, just kind of do with that what you will. So we've talked a lot about varieties in the context of Grosvenor bases. We're going to define them really rigorously now, and we're going to talk about the Zariski topology. We ended with that last time, but now we're going to talk about it a little bit more in the context of AG. So number one, I guess before I go into Hartshorne, let's review from last time. So a topological space is something which satisfies these three things. So it's a collection of subsets of a set, and we call the elements of the topology open sets. Those open sets follow these three things. Metric spaces are an example of topologies. Even though we are working in what is kind of the ambient metric space of the complex numbers, or mixed characteristic fields, we're actually not going to use metric topology a whole lot. And so that's because we're going to define a Zariski topology. We talked about category theory. I'm going to try and just sprinkle in. I found a really great lecture series that goes through Vakil, and they skip chapter 1 of Vakil and just kind of sprinkle it in when they need to. I'm going to try and do the same thing. But yeah, so the Zariski topology is the one that we're really going to care about. We'll talk more about that tonight. But essentially, it is open sets are the complements of algebraic sets, which of course includes varieties. We also talked about the product topology and the subspace topology. And then, yeah, the Zariski topology is this. We recalled the notion that basically, in affine one-dimensional space, the Zariski topology is the cofinite topology. So open sets are the complement of finite sets, and so finite sets are closed. And we talked about, what functions are continuous in the Zariski topology on C. And so we said, okay, topological continuity, F from C to C is continuous if and only if inverse images of open sets are open. But then equivalently, it's continuous if every closed set has, in the codomain, has an inverse image that's closed in the domain. And this just follows as the contrapositive of topological continuity. And so we showed that non-constant polynomials are continuous in the Zariski topology. And what we didn't say last time is actually those are the only functions that are continuous maps in the Zariski topology, on one dimension or any dimension. And so, yeah, we really just kind of care about polynomials. So the Zariski topology is nice because it isolates polynomials. We also talked about regular functions. Regular functions are polynomials which can be represented as the quotient of two other polynomials. And just kind of a food for thought thing, I was typing up a paper for one of my classes on this topic, and I kind of wanted to say that for rational functions to be continuous in the Zariski topology, we need h of x in the denominator here to not zero out anywhere, because otherwise we run into problems. And so basically, a rational function is only continuous if it's regular, meaning that g of x is perfectly divided by h of x. And so then the theorem that we're going to build up to is kind of like our big thing that we care about, just as like a first cool thing in algebraic geometry, is that if you have an affine variety, you have an open subset in the Zariski topology on this affine variety, then these two functions, if they agree on the open subset, they agree on the entire variety as well. And so this is kind of what's called a gluing theorem. And this is maybe the first checkpoint I want us to be thinking about, is like where we're going with all of this for now, is we want to be thinking about local to global constructions and how we can generalize like regular functions agreeing on a subset, generalizing to an entire variety. Okay, so having said all of that, we're going to start with some definitions, because nothing says introduction to whatever like an entire board of definitions. Okay, so, and I'm also, even before we start definitions, I'm going to start with some conventions. And these are going to hold basically unless I say that they don't for the foreseeable future. So K is always a fixed, algebraically closed field. And so this means that if we have polynomials over K, we don't need to add stuff to K to make all of the roots of the polynomials end up back in the field. The Galois group of any polynomial in K is the trivial group. We will also define the affine n space over K. So this thing an over K is equal to an is the affine n space. And this is really just all n tuples of K. And the way you can think of this is like you have like A0, A1, A2, dot, 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 AN, where AI is in K. And there's this really great explanation I found from another algebraic geometry seminar run by some students at, I'm pretty sure MIT. But basically, the way that they explained affine n space is that it's very similar to a vector space. In fact, a vector space and affine space are very closely identifiable because you can have kind of a forgetful functor back from affine n space to a vector space. Because where a vector space, if we're like consider the complex vector space of dimension 1, well, that is just all of the matrices with strict elements in the complex numbers, whereas the affine variety over C in dimension 1 is actually defined by matrices of the form A and then 1 and whatever up here. And so the idea is that we add on this extra stuff because this gives us a property of translational invariance. Hartshorne doesn't talk about this, and it actually really only clicked for me when I heard this guy talk about it. So I want to really emphasize that here I am a student, I am learning a lot of this stuff, and so it's very possible for me to get things wrong. So if something doesn't make sense to you guys, please call it out immediately, and we can sit and talk about it for as long as we need to figure it out. Because if something smells fishy, it probably is. But yeah, so affine n space is this thing that basically appends this 1 down here. And what this lets us do is this gives us translational invariance. And the way the folks at MIT talked about it is they said that there were like 2 columns. Things which make sense in affine space, and then things that don't. And so this is kind of the idea of like translational invariance. Affine n space is the set of all of the things which are translationally invariant. So things that don't make sense are like squares, because you could very easily transform a square into a parallelogram. And so kind of the idea of the affine, like that's a linear transformation. Anything that can be transformed by a linear transformation is not preserved, right? So in the same way, like circles, wow, I can't spell. But circles are also like not preserved because you can very easily turn them into ellipses. Forgive the poorly drawn ellipse. And really the idea that we're getting at here is that angles don't make sense, right? And I think the 2 above cases are perfect proof of this. Like the square idea, like that angle is not preserved. And so the big difference between a complex vector space and an affine space over C is that we don't preserve 0. Affine space doesn't preserve 0 because we have this extra column that basically lets us move 0 around. Things that do make sense. Anything that is invariant under linear transformations. I'll also add, in addition to 0, and really in addition to angles and magnitude. Again, we can transform like a very small square into a very large square linearly. So magnitude and angles really are not preserved in affine n space. Now, this is not the same thing as projective space, because what projective space does is it, and we'll talk about this next session, hopefully, unless we don't get through all this chapter. Projective space identifies everything to a homogeneous point. So it's a set of equivalence classes of like, you know, things at a certain ratio of functions with respect to other functions. I don't think that's a great explanation of it, but in terms of like what affine and projective space differ on, affine space focuses on like giving linear transformations to things. Projective space focuses on preserving the ratio between functions. Yeah, Arseni.
So how much does it have to do with eigenvalues and eigenvectors?
That's a good question. Well, so that's a very good question. So I'll use the example of the circle here. So have you guys seen like pictures with principal component analysis, where it's like you have the vectors and then like the eigenvectors and the eigenvalues. The eigenvectors tell you like the directions of the ellipse that build the ellipse out, and then the eigenvalues tell you like how far it spans out around things. So principal component analysis, and of course eigenvectors and eigenvalues, very much have to do with telling us kind of how much something has been changed under a linear transformation, right? linear algebra is about linear transformations, and so it makes sense that like we are taking the standard basis and we are moving it in the direction of the eigenvectors with the magnitude of the eigenvalues. This is where like the spectral decomposition comes in from linear algebra. And so they're kind of like our prime example of stuff that is not preserved. And like if you think about the singular value decomposition or the spectral decomposition, those both motivate the fact that like either you have like this normal matrix that's full rank and does everything that you want it to with eigenvectors, eigenvalues, and that's not preserved, or you have like this other thing, which is not full rank but is still nonetheless unpreserved in affine space, and that happens because we can move zero around like it's doing a linear operator on it. Does that answer your question?
Yeah.
Okay, cool. So any element of affine space we're just going to call a point. And so yeah. And then each of these, like this is like a point. I'm also realizing it's not that, it is that. So it's A1 to AN. So those are called like the coordinates of the point. This is not the same thing as the coordinate ring. That we'll talk about that later. And so then just as long as we're keeping up with the whole convention thing, so we're going to let A be the polynomial ring over K, right? So it has n variables, and that's just kind of what we're looking for. And really, they're functions that take like f in another convention. This list I'm going to abbreviate by like a capital X. Any polynomial in here is a polynomial from points in the affine space to K. So remember, K is an algebraic closure, and then the affine n space are just all the points which we can throw through these polynomials, and so this works kind of exactly the way we would want it to. So we've talked before about algebraic sets, but I'll just reiterate the definition here. So since K is a ring, K has to have 0. And really, since K is an algebraic closure, like we know it has a 0 that's well behaved. And so because of that, we can talk about roots of polynomials. So Y, which is a subset, the affine n space, is an algebraic set if and only if there exists f1 through fs in the polynomial ring such that the 0 set of f1 through fs, which is the set of all p in an such that fi of p is equal to 0 for every I, is equal to y. So basically, they're all of the shared zeros of whatever we throw into this thing. Now, last time we talked about the Zariski topology. I'm just going to throw out there, whenever we talk about the topology on a variety, we're talking about the Zariski topology. Unless I explicitly say otherwise, the Zariski topology is our new standard topology. And its open sets are the complements of these algebraic sets, and its closed sets are the points of the algebraic set. Everything that we're going to do hinges on this idea of algebraic sets and then whether or not they're closed or open. So like one example of something that is surprisingly open and closed simultaneously is the entire space of the complex numbers, because we can have a constant function and its preimage is just all of C. Keep in mind, we're taking K to mean C for most of this stuff. Hartshorne talks in total generality, at least for characteristic 0 algebraic geometry. I can't speak for characteristic P. But for characteristic 0 algebraic geometry, he's talking completely just abstractly. We're going to think about examples over the complex numbers. Mostly because there are a lot of nice properties we can bring in from complex analysis. So, yeah. So before I hit the next definition, there's a proposition Hartshorne has that is just important for proofs. The union of two algebraic sets is an algebraic set. The intersection of two algebraic sets is an algebraic set. And then the empty set and the whole space are algebraic sets, and that goes without saying. But yeah, so the empty space and the entire set, or sorry, the empty space and are algebraic sets. And actually, I probably shouldn't say C here, but I should just say K. Nope, not K. AN. So now we can define the Zariski topology. So the Zariski topology on AN is the topology defined by open sets are the complements of algebraic sets. And then, of course, closed sets are precisely the algebraic sets. And this is clearly a topology because basically by this proposition, the union of any two algebraic sets is an algebraic set. The intersection of any two algebraic sets and of any family of algebraic sets is an algebraic set. And the empty space and the whole space are sets. So, yeah. I guess I'll put this as like an example. He has this as example 1.1.1, but what I'll say is that in the affine line A1, this is basically going to have us have A is equal to the polynomial ring in one variable. And this is a principal ideal domain. What that means is that every ideal is generated by one thing, and so every algebraic set is the zero set of a single polynomial. All of these are equivalent statements with our Grosvenor bases, so if you want to go back on your own time and think about that, that might be helpful to get some intuition here. But then, yeah, so f in k over x has f is equal to c times x minus a1, x minus a2, dot, 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 x minus an, where n is the degree of the polynomial. And so then the zero set of f are just a1 through an. And so then the finite subsets of this zero set are the closed sets. And then, yeah, the open sets are non-finite subsets of ZF complement for every such F. So is this example clear to everybody? Okay. So now we get to another definition, which is that a non-empty subset Y of a Zariski space, and really a topological space, but we'll just use the affine n space. It's irreducible if there do not exist y1 and y2, which are closed in y. So I'll actually write that out. Closed in y, where y is equal to y1 union y2. And so I'm just going to throw out there y itself is closed when we're talking about algebraic sets. And so this set, like algebraic sets being irreducible, is this issue of there are not other closed sets which make up y. And so this leads me to the big definition of the night, is that y in an affine n space is a variety, really an affine variety. I'll specify it because we're going to talk about other kinds. Is an affine variety if and only if it is an irreducible algebraic set. So putting it all together, it is a closed set in the Zariski topology, which cannot be decomposed into a union of other closed sets. So on the affine line, let's just think about this for a second. If we have, something like we had in our first example up here, where the closed sets are, like A1, A2, dot, 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 AN, if that's Y, well, there are definitely other closed sets, namely the polynomials, which are, F1 is equal to x minus A1, F2 is equal to x minus A2, Fn is equal to x minus An. Well, each of these generates a closed set, and these sets are algebraically irreducible, whereas Y can be decomposed into these irreducible sets. And so Y is not a variety. But the algebraic sets generated by F1 through Fn individually are. So like the zero set of F1 or Fi is an affine variety. And I'll mark this as example in A1. Keeping in mind this is not largely true, right? My example for something that like looks like y that's in a higher dimension and is not finite has, f is equal to xy. Well, this zeroes out when y is 0, and it zeroes out when x is 0. So we actually have two copies of k that make up our variety, and that's definitely irreducible because we don't have any other algebraic sets that we can like pull together to get that. Yeah. So the entire affine line is also irreducible. When we say A1, that's what I mean. So affine line. And then any non-empty open subset of an irreducible space is irreducible, and its closure is equal to the entire space. We won't prove that though. That's just like a topology proof. Yeah, and so then second definition. So yeah, y is a quasi-affine variety if and only if it is an open subset, note open, of a variety X in AN. So again, breaking this down, so affine varieties are closed irreducible sets. Well, quasi-affine varieties are open subsets of closed sets, which are also irreducible. No, it actually doesn't have to be irreducible. It can just be an open subset. So anything that is the complement of of another polynomial, basically. So like if you have a variety that's generated by a polynomial or a set of polynomials in affine n space, and then that's closed, say it's also irreducible, then any open subset of it is maybe like the complement of all but one of the polynomials, right? Well, that's an open subset in the variety because the variety is the ambient space. So like if x is equal to the zero set of f1, fs minus 1, fs, then maybe the zero set y is equal to the zero set of f1 through fs minus 1 is equal to x set minus the zero set generated by fs. And so x is a variety, y is a quasi-affine. And I'll actually clarify variety over here on the left is an affine variety. So does this definition make sense to everybody? If not, I should know so that like we can cook up some more examples.
What is that notation on the
Here?
yeah, right there.
Yeah, so it's x set minus z.
Okay.
Yeah, so it's all of x. It's basically z of fs complement, right? But I'm specifying that the ambient space is x.
Okay.
So it's not an, right? Because if it were just an, then like y wouldn't be an open subset of x. But we're looking at open subsets of varieties, not of the affine n space.
Okay.
That's a good question. Any other questions? Okay. So, we're going to define the ideal of a variety. We did this already with Grosvenor bases, but we're going to look at it again. And then we're just going to revisit some things that we talked about at length previously that Hartshorne spends all of a paragraph on. And this is kind of like the first culture shock of like a graduate textbook. But yeah, so if y is a variety, I guess, and this doesn't even just hold for varieties, but it can be any subset. So y subset of an has the ideal generated by y is the set of all polynomials in our polynomial ring such that f of p equals 0 for all p in y. And so if this is a variety, this is nice. We have talked at length about the properties of ideals of varieties. We've talked about finding better generators for them. But yeah, I mean, this is like just very nice. And so this leads to a proposition that basically sums up a lot of what we've done already, which is the reverse inclusion lemma. So if T1 contained in T2 are subsets of A, which is our polynomial ring, then the zero set, the algebraic set generated by one contains the other. And so this is reverse inclusion. We proved this, I think, in lecture 2. So if anybody didn't catch that, that might be helpful to see. So if y1 is contained in y2, which are contained in the affine n space, then the ideal of y1 contains the ideal of y2. And again, this is also reverse inclusion. And it doesn't look like reverse inclusion from A, but if you chain it together, it ends up being that, right? So if y1 is a subset of y2, then that means we're talking about z2. So just putting that over here, it isn't obvious from the way that it's written. But again, it's just kind of inclusion reversing back and forth. Okay, so C, so for every y1 and y2 subsets of the affine n space, the ideal generated by y1 union y2 is equal to the ideal generated by y1 intersect the ideal generated by y2. And we didn't talk about this one, but this just follows directly from A and B. This fact literally just follows from the reverse inclusion lemma and De Morgan's laws. But yeah, I think that's a given. And then so D, for every ideal, they use A. For every ideal A subset of our polynomial ring, the ideal generated by the zero set, which is generated by that ideal, is the radical ideal of A. And more on this in a second with Hilbert's Null-Stellensatz. And actually, no, I'm just going to go ahead and plop that definition in. So square root of A is equal to the set of all f in capital A, which is our polynomial ring, such that f to the r is in A for some r greater than 0. So it's not guaranteed that it's all R. In some cases it is, but in lots of cases it's just one specific R that gives us this radical property. And then finally, part E, for every subset Y contained in the affine n space, the zero set of the ideal generated by Y is the closure of Y. Keeping in mind that the closure just adds the boundary points of the set to it. And so from this we can state this big kind of like first theorem. Like if you ever say, oh yeah, I'm studying algebraic geometry in my free time, they're going to say, oh, tell me about Hilbert's Null-Stellensatz. So here we go, Hilbert's Null-Stellensatz, and then you guys can tell me, hopefully, where we've seen this elsewhere in our Grosvenor basis section. So Hilbert's Null-Stellensatz. And so what it says is let K be an algebraically closed field, and then let A be an ideal in A, which is our polynomial ring. And then let F be in the polynomial ring such that F vanishes on the ideal or on the zero set generated by this ideal. So basically it's in the radical ideal. Then there exists f to the r in A for some r greater than 0. And I don't know how to prove this. Hartshorne references a commutative algebra textbook called Atiyah McDonald, which I've heard some really great things about, but I don't have a copy of, so I can't prove this. But maybe it's a good exercise to do between now and when we meet next, to try and prove the Null-Stellensatz, or to look up a proof and annotate it or something. So any questions about the Null-Stellensatz? Okay. So I'm hoping that this is some stuff that, people are feeling comfortable with. It's just new notation for things that we've talked about in previous lectures. Now, there's a corollary of this. There is a one-to-one inclusion reversing correspondence between algebraic sets in the affine n space and radical ideals. And then furthermore, an algebraic set is irreducible if and only if its ideal is a prime ideal. And so, yeah. Yeah. Let me make sure. Hold on. I want to make sure that there wasn't anything. I think there was something else I wanted to cover right here. Yeah. Okay. So, okay. Yeah, that's what I wanted to cover here. Okay, so really I care about the second part of this proposition, which is that an algebraic set Y in affine n space is irreducible if and only if the ideal generated by Y is a prime ideal. And then for those who maybe are not fresh on what a prime ideal is an ideal generated by irreducible polynomials in K. So notably, since K is an algebraic closure, in one dimension, these are all of the sets that are like x minus a, right? And we saw that when we were talking about the affine line. This is the thing that forces varieties to be singleton sets on the affine line. And then the proof is actually not bad. So we're going to do it. And then we're going to go through some examples. So let Y be irreducible. And then we want to show that the ideal generated by Y is prime. And so we want to let the polynomials fg, or rather the product fg, be in IY. Then Y, by reverse inclusion lemma, is contained in the zero set of that polynomial. But then up here by part C, we know that this is really the zero set of F union the zero set of G. And my example for this, just to make this make sense, is this. Right? The algebraic set generated by the polynomial xy is the zero set generated by x union with the zero set generated by y, which gives us two copies of the affine line. And so then, and this is kind of where there's a bit of a leap, y is equal to y intersect the zero set of f union y intersect the zero set of g. Which are both closed in Y. And then since y is irreducible, this is a contradiction. And basically the contradiction is drawn from y must either be contained in the zero set of f or in the zero set of G. But that can't be true by contradiction. So accordingly, we've shown direction 1. Any questions on this direction of the proof? Okay. So now for part 2, let P be a prime ideal with the zero set of this ideal equal to y. So we're saying y is an algebraic set, or sorry, y1 union y2. So we want to show that y is irreducible. Well, then P is equal to the ideal generated by y1 intersect the ideal generated by y2. This is a big line. Does everybody get this line? Like where this comes out of? So basically it comes out of part C. So we're saying the ideal of the union is equal to the intersection of the ideals.
It's kind of like the fundamental theorem of finite abelian groups.
I mean,
or was it the Galois theorem? Which one was it?
Not really.
It had to do with inverses.
The Galois, the fundamental theorem of Galois theory had to do with the inverse containment of the set phi and the set E, which has to do more with fields than it has to do with this.
Okay.
Yeah. But yeah, so here we're talking about just varieties, which is kind of a different algebraic structure. But yeah, so part C is the thing that really motivates us here. So we get that it's the intersection of the ideals. And then accordingly, so P is either equal to the ideal generated by y1 or P is equal to the ideal generated by y2. And then that just means that P then ZP, sorry, zero set of P is either equal to y1 or y2. So irreducible. So what we've gone through is we've said, okay, assume that it is in fact reducible into y1 and y2. The zero set is reducible into y1 and y2. Well, then its ideals have this containment thing, but since P is a prime ideal, we know that it has to be just one of these things. And that's what it means really for it to be a prime ideal in this sense. So I'm just going to color code this proof. It's an ugly color. There we go. So ZP of y1 or y2, or union y2, becomes that it has to be one of them. And then similarly, P being a prime ideal comes down to this line here. And then this line comes from part C. So that's where we pull this part of the proof out of. So any questions on this? Okay. So then, just some examples that fall out of this theorem. The affine n space is irreducible since it corresponds to the zero ideal. Right? So this is kind of like the reverse containment thing between ideals and varieties. And then if we have a polynomial that's irreducible in k over x and y, so f irreducible in k over, let's just say x and y, then f generates a prime ideal. In k over xy. And then y equal to the zero set of f is irreducible. And then kind of an example that we'll lean on in the future, we call f equals 0 the affine curve. And then we really also say that it is of degree d, where d is equal to the degree of f. And so again, it really doesn't matter what polynomial we use for this, because just thinking back to how we started this when we were talking about affine space, anything that is linearly translationally invariant is what we care about. But angles aren't preserved, and so the angles of tangent lines on affine curves are not preserved. So basically, and this is kind of to the point of homotopy, I know you guys, all three of you actually were asking about it. So homotopy is this idea that if you have two curves, f1 and f2, you can continuously turn one into the other. There is no better example of homotopy than in affine n space between affine lines. Because since any two curves in affine n space are immediately homotopic to each other by the fact that we can move them around to each other and curve them kind of at will, by using linear transformations, we get what's called the straight line homotopy between f1 and f2. And so this is kind of where algebraic topology takes off. As algebraic topology says, okay, this homotopy thing is cool. How can we generalize this to basically tell us like what path homotopies and loop homotopies can't get around? Like if there's a space, or if there's a part of our space where there's just like this hole that we cannot go around, then the homotopy class goes up by 1. And so you can compute this a couple different ways, but kind of the way that algebraic topologists like to use is called homology and cohomology. And we'll talk about that actually pretty soon. So we're going to do the first 7 sections of Hartshorne, then we're going to switch over to Vakil. And as soon as we start doing Vakil, we're going to start talking about homology and cohomology. And really, that's like the frontier of modern algebraic geometry is cohomology theory. And so what I would really like to do, and kind of like where I want to steer this to go towards, is I want to talk about derived categories and cohomology theories on derived categories. But yeah, so this is like homotopy. And then the idea of the affine curve of degree D is basically the degree actually defines uniqueness of curves in affine n space. This is kind of where it comes in to be useful for like thinking about computer science stuff or data science. Is we like to think about this property of affine translational invariance in terms of its algebraic structure and the ideal generated by its zero set. So when we're thinking of this affine curve of degree D, we're really thinking about the ideal generated by its variety, and then we can kind of find easier ways to compute things with like weird data sets defined by its homotopy class. That's where like persistent homology algorithms come in topological data analysis. So yeah, more generally, like from this, if f is irreducible in n dimensions, then instead of an affine curve, we have an affine surface. And basically, if n is greater than 3, it's called a hypersurface. So if I ever say hypersurface, it's just a three-dimensional version of this where it's an irreducible polynomial in n dimensions. And then this is an important definition that Hartshorne really glosses over, but shows up later. So M in A is a maximal ideal. And I want to make sure that I get the definition right, so I'm actually going to Google this real quick. Yeah, so M is a maximal ideal if and only if there does not exist an I subset A such that M is a proper subset of I is a proper subset of the polynomial ring. And then like a little lemma about maximal ideals. And really there's quite a few lemmas about maximal ideals. This is kind of where doing a little bit more abstract algebra will help. But basically maximal ideals correspond to a minimal irreducible closed subset of AN, to a minimal irreducible closed subset of AN, which must be a point. And so I really can't stress this little thing enough. So later on, we're going to talk about the localization of a ring of regular functions on a variety. And that has heavily to do with maximal ideals. But you know how, and this is going to seem totally off the cuff, you know power series? Like from Calc 2? Yeah. So a space is called Cauchy complete if all Cauchy sequences converge in the field, or in the space, really. A space is complete algebraically if all of its power series converge. And in number rings, that happens to be Cauchy series or Cauchy sequences. But in polynomial rings, convergent power series are actually our way of defining that something is a complete space. Moreover, we can pick out any convergent power series, and we can actually divide by that ideal in like a quotientine kind of way. If you're familiar with that from algebra, from abstract algebra, or like algebraic topology, or even topology with quotient spaces, we can kind of quotient out by that, and it's called the localization at that ideal, or like a localization at a polynomial, which is irreducible. And so the idea with that is that like it has to be this minimal closed point, or it has to correspond to a minimal closed point. It acts as like this infinitesimal thing, which does not have the Archimedean property. And we get a lot of mileage out of that later on. So this is like a very small line in Hartshorne, but it's a very important line. Notably, like if K is not algebraically closed, none of this holds. And the reason why is because if you have stuff, if you have polynomials in your polynomial ring, which have roots outside of K, all of this is dependent on the idea that all of your roots lie within K and can be closed subsets of A to the N. And so you need to have algebraic closure for any of this to really work. And then this is, I'm going to put this in red because it's so important. So if Y contained in AN is an affine algebraic set, meaning that it just has the same affine properties and it happens to be an algebraic set, we define the affine coordinate ring A of Y to be A of Y is equal to A quotient the ideal generated by Y. And notably, the affine coordinate ring of a variety is Y, or is A quotient its maximal ideal. So the affine coordinate ring of an affine n space is actually basically A of AN is equal to A quotient M, where M is a maximal ideal. And what this is this is actually the residue field. So sometimes this gets the other name as the residue field. Because this gives us just a copy of the underlying field. If K weren't algebraically closed and we wanted to get a version of it that was, this is how we would get it. Is we would say, okay, take your affine n space over a non-algebraic closure, find its maximal ideal or some maximal ideal of the polynomial ring, take this quotient space, we call it the residue field, it has to be algebraically closed. Because we're quotienting out by all of the polynomials which are closed and leaving an equivalence class of the ones that aren't. And so, yeah, a few remarks about affine coordinate rings. I'll call this remark 1. Then remark 2 is that if Y is an affine variety, then the coordinate ring of Y in A is an integral domain. And again, just reminding everybody, an integral domain is a ring with no zero divisors. So like we can't have like 3 times 2 mod 6 is congruent to 0. We can't have that if it's an integral domain. So like finite fields are an example of this. Although you can have integral domains which aren't fields. I think like tensors are a good example because they're non-commutative. Or like the quaternions are an example. It's a non-commutative ring. It has no zero divisors, and it is finite, or it can't be finite. Okay, so remark 3 is that A of Y is a finitely generated K algebra. And you can really just think of a K-algebra as a well-behaved module with coordinates in K. Well-behaved module. So like one example of this is like a Z algebra is a module which has bilinear multiplication. So you can distribute things on both sides. Um, so yeah, and then any finitely generated K-algebra, which is an integral domain, is the affine coordinate ring of some affine variety. And so like that can kind of just work nicely. So what we're going to finish off the night with is we're going to look at the topology of varieties. And what we're going to do is we're going to introduce a class of topological spaces, which includes all varieties. Then we're going to talk about dimension of varieties and dimension of algebraic sets. The reason why that's so important is it lets us kind of force geometry together. And then, yeah, that's what we're going to end with. And I'll give some exercises to think about until Monday. So, yeah, starting off, so definition. A topological space X is a Noetherian topology. If it satisfies the descending chain condition for closed subsets. And so the descending chain condition, of course, is kind of worth its own definition. So the descending chain condition says for every sequence y1 containing y2 containing ... of closed subsets, there exists an integer r such that y sub r is exactly equal to y sub r plus 1, and so on off to infinity, meaning that there is like a smallest closed subset. But the important part is that we can have a countably infinite chain of these closed subsets. And this is actually something that we're going to use later when we talk about homology and closed homology in like these things called long exact sequences. And so, yeah. Now, it's worth noting affine n space is a Noetherian ring, or is a Noetherian topological space. And A, which is the polynomial ring, is a Noetherian ring, which I believe means finitely generated. Let me just double check that there aren't any subconditions. Yeah, every ideal is finitely generated. Every ascending chain of ideals stabilizes. Every non-empty set of ideals has a maximal element. So I'll list that out because that's important. So every ideal is finitely generated. This is yeah. And then 2, every ascending chain of ideals stabilizes, and that's the same idea as what we talked about above, except instead of being closed subsets, they're ideals. And then 3, every non-empty set of ideals has a maximal element. A maximal element. And so then our next proposition is that in a Noetherian topological space, every closed subset can be expressed as a finite union of irreducible closed subsets. And this just falls literally right out of the definition that we just gave. And so we call those things the irreducible components of that subset. So in a Noetherian space, keep in mind space, not ring, space X, every non-empty closed subset Y tangent X can be expressed as a finite union Y is equal to Y1 union dot 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 YR. Where if none of these contain each other, right? So they're all disjoint, or at least partially disjoint. Then each yi is uniquely determined. Yi are the irreducible. Wow. I cannot spell. Components of Y. Now, who can, brownie points here, brownie points up for grabs, who can tell me why we care about the irreducible components of Y? Better yet, who can tell me why we've been working with them this whole time and like why this should be a very intuitive thing about affine space for us? So I'll give a hint. When we're thinking about varieties, what makes a variety different from an algebraic set? Well, a variety.
Irreducibility.
Yeah, so a variety is an algebraic set which is irreducible. And so more importantly, this means we can take any subset of our space and we can break it into varieties. Right? So it may not even be an algebraic subset, right? We can take any subset. We can reduce it not only into algebraic sets, but into varieties. And we can do it finitely. So we can like have a finite generation for every subset, including the whole space of a Noetherian space. And by and large, we will work with Noetherian spaces because they're well behaved for this exact reason. Yeah, so this is corollary 1.6. Every algebraic set, and like we just said, every subset, but here they say every algebraic set just to emphasize it, can be expressed uniquely. That's the other piece. The unique piece is important. As a union of varieties, none of which contain each other. So now we get to this idea of dimension because we have this unique expression of every algebraic set. We want to say that the dimension of an algebraic set is basically the supremum of integers which define this chain of irreducible closed subsets. So formalizing this, so X, a topological space, then the dimension of X is equal to the supremum of all integers 1 through n, such that there exists Z0 contained and Z1 contained in Zn of, and I'll just say that there exists a chain of distinct, irreducible, closed subsets of X. And then the dimension of an affine or quasi-affine space is its dimension as a topological space. So for example, the dimension of the affine line is 1. Its only irreducible closed elements are the whole space and singleton sets. And any chain that you can construct there has to be, any finite chain you can construct has to be of length 1. Obviously, it gets a little bit more complicated from there. In a ring, so this is kind of our next definition. In a ring A, the height of a prime ideal P is basically n in Z such that there exists a chain of ideals P naught contained in P1 contained in up to Pn, which is equal to P of distinct prime ideals. And then the dimension of the ring is equal to the supremum of the heights of prime ideals. And really, this is of all prime ideals. So does this definition make sense? Does everybody know what a supremum is? Okay.
Could you explain that, Tim?
Yeah, so the supremum is the least upper bound of a set. So people kind of interchange least upper bound, supremum, at will. Supremum sounds fancier. I don't think there's a difference, at least none that I've encountered. but I'm 20, so who knows? Yeah, as far as I know, it's the same thing. But yeah, it should be least upper bound of the heights of prime ideals. So, proposition 1.7 says that if Y is an affine algebraic set, then the dimension of Y is equal to the dimension of its affine coordinate ring. So notably, this dimension is the dimension of it as a topological space, right? So dimension as a topological space. This is its dimension as a ring. And these two things line up. And the proof of this is actually pretty easy. The affine algebraic sets correspond directly to prime ideals or a product of prime ideals. And so it's like just literally just almost like the fundamental theorem of arithmetic. All numbers are either primes or the product of primes. It is the dimension that the affine coordinate ring is constructed of chains of prime ideals. And so basically the longest such chain is equal to the longest such chain of distinct irreducible closed subsets. This idea of primality is actually very in touch with the algebraic structure in number fields, polynomial rings, and topological spaces, that really all three go together. So we've got just a little bit more to go in this. So theorem 1.8a is two parts. So we already have K as a field. Let B be an integral domain. Which is a finitely generated K algebra. Keeping in mind that a K algebra is a module with bilinear distributive property multiplied, meaning like you can multiply across sums from the left or the right and get the same thing. And otherwise it's a module with coefficients in K. Keeping in mind that a module is a vector space. Yeah, Dr. Scott.
I just have a quick question. It doesn't make sense to say that the algebraic the varieties span the algebraic set. That doesn't make sense in this situation, right? I'm just trying to learn by analogy, so I'm just
it's actually very close. I don't think it's the technical word to say that they span. I think from like it's the word isn't physical, but like from a physical understanding of what it looks like the basis of a topology spanning the topological space.
got you.
Yeah, so if you know like what the basis of a topology is, it's the same exact idea of like the basis of a topology spanning the topological space, except the word that we would use isn't exactly spanning because it's a set of like it's a chain of containing ideals or containing algebraic sets.
Got you.
But yeah, you're on the right intuition for sure.
Thank you.
Yeah. So we have this integral domain, which is a finitely generated K algebra. Our first part of the theorem is that the dimension of this finitely generated K algebra is the transcendence degree which is defined by the ring of fractions of K, B, or of yeah, it's the ring of fractions of B over K is the transcendence degree of the quotient field K B of B extend K. I think that this is the right way to express it. So K of B is the field of fractions. I think that that's right. I'm not actually sure I understand this one. So I'm just going to put a little star. I'm just going to say not sure I wrote this right. So feel free to email the email chain if you figure this one out or figure out that I was right or wrong, because I'm not sure I actually get that one. But two, I do know I get for every prime ideal P in B, the height of P plus the dimension of B quotient P, B mod P, is equal to the dimension of B. So for people with linear algebra background, this is like kind of our equivalent of the rank nullity theorem for finitely generated K algebras. So B is this polynomial domain. P is a maximal ideal of that. And so then the height as a polynomial ideal. The height is a polynomial ideal plus the dimension of the quotient is the dimension of B. And the example of this that I have written down in my book that I wrote down is that Q over X quotient, the ideal generated by x squared plus 1 is isomorphic to Q adjoin I. And so, like, this is a Q algebra, so to speak, right? And it's finitely generated by 1. And so we can pick a prime ideal, and then the height of the ideal is 1. And the dimension of the quotient space is 1, but then the dimension of the ambient space is 2. Because you have your number field, and then you have everything in variable x. The other example that Hartshorne has is that the dimension of the affine n space is n. And this just kind of follows from the way that we set up affine n space, right? So there's another proposition that has to do with quasi-affine varieties. So if y is a quasi-affine variety, then the dimension of y is equal to the dimension of y closure, meaning that as a topological space, when we close it, we like get this chain of closed subsets. We actually already contain everything that we need. And this is because y is a quasi-affine variety. It is an open subset of a closed space in the affine n space. Hartshorne has a good proof for this that's not super long, but I need to end a little early tonight. So it's on page 6 for anybody who wants to go and read it. I would recommend going through it if you own a copy of Hartshorne. Maybe it's available online. I haven't looked. Definitely worth having, though. And so the really big theorem that Hartshorne ends this section with is called Kroll's, and I'm gonna mispronounce this, so I'm gonna write it first. Hoptide shots. It's kind of funny, as part of Princeton's admission process, and like their qualifying exams, you have to be able to translate a paper in your field in either German, French, or Russian. So I'm trying to learn German right now, and rather, I'm trying to learn math German. And so I've been doing this in two ways. I've been watching lectures in German from the 1980s, from MIT, and then two, I've been listening to this metal band called Rammstein. And so at the end of this process, the only German I'm going to know is going to be German EDM metal and anything that is in MIT's lecture series from the 1980s that happened to make it onto YouTube. And I really think that that's beautiful. So yeah, anyway, Kroll's Hauptideal shots. This theorem says let A be a Noetherian ring. And let F be a polynomial in this polynomial ring such that F is neither a zero divisor or a unit. And when we say unit, we just mean a thing that acts like one, but might not be one. You can imagine that if we have an affine space that removes the concept of zero, we might get multiple concepts of one that all happen to work. An example of this is if you're taking a ring homomorphism from the complex plane into the modulus of points in the complex plane, anything that lies on the unit circle acts like a unit in the polynomial ring over C in one dimension. So that's just like one way to look at it. And yeah, then the implication of this is that then every minimal prime ideal P containing F has height 1. Meaning that the only chain that exists for minimal prime ideals is composed of these things which are neither divisors nor units. And so in that way, this is actually like a very implicitly geometric construction. We'll probably start by thinking about this next time. So there's two other propositions. I'll just write them down, and I just kind of want you guys to think about them before Monday. So proposition, a Noetherian integral domain. Noetherian A is a unique factorization domain if and only if every prime ideal of height 1 is principal, meaning that it is generated by one polynomial. So an Noetherian integral domain is this thing which satisfies the descending chain condition. A is a unique factorization domain, meaning that everything factors uniquely and everything can be factored. If and only if every prime ideal generated by reducible or by irreducible polynomials of height 1, every chain of prime ideals has one thing in it, is principal, is generated by one thing. So translating all of that, it might be good to, like, for yourself, walk yourself through talking through that sentence. And then another proposition, our final proposition of the night, is that a variety y in the affine n space has the dimension of y is equal to n minus 1 if and only if there exists f in A, which is a non-constant and irreducible polynomial with y's the zero set of f. This is where it all comes back to where we started and where we finished last time, where we were talking about continuity of polynomials in the Zariski topology, right? What was our whole deal with continuity in the Zariski topology? Non-constant, right? So this is continuous in the Zariski topology from AN to AN. F is in A. Okay, cool. We have this thing that is continuous. The zero set of continuous polynomials in the Zariski topology, the varieties generated by those things have dimension n minus 1. And really what this is saying is if you think back to when we first started talking about affine n spaces, the way we described them was with this matrix. Dimension n minus 1, that just means it's just this A. So if we have a continuous polynomial in the Zariski topology, the variety generated by that polynomial has a notion of 0, even though it's in an affine n space. And that preserves angles. So in affine n space, we actually now have a way to preserve the angles of things. Okay, so that's all I've got for you tonight. Any questions before I turn off the recording? Okay, so I'll email out some problems and some pictures of the problems that Hartshorne has. Next time we'll talk about projective varieties. It'll be on Monday. I will send out a time. It may be not, I don't know. We'll figure out the time. I'll send logistical email updates for it. Please take a look at the homework problems that I'm going to send out because you'll just kind of get a lot out of it. So anyway, I hope that this has been helpful and interesting for everybody. And that, yeah, welcome to your first real lecture on algebraic geometry. That is not a small thing. So, okay. Have a good night, everybody. I got to... And then I guess for the three of us, so for the research project that you wanted